What if everything you thought you knew about curves, straight lines, maybe even how gravity works, was only half the story? We often think of mathematics as perfectly precise, right? But what if our everyday intuition, and maybe even the laws of nature, actually operate on a fundamentally different level, sort of approximate? Today we're taking a deep dive into the fascinating world of Felix Klein's elementary mathematics from a higher standpoint. And our mission really is to unpack his core distinction between precision mathematics and approximation mathematics. We want to reveal how it sheds light on, well, everything from abstract numbers to the actual shape of the Earth. Think of it as a shortcut to understanding the surprising gaps and also the powerful connections between these ideal mathematical concepts and our messy observable world. Now, this deep dive is based on a foundational work by, one of history's greatest mathematicians, Felix Klein. His insights, they were translated nearly a century after he first wrote them, but they remain remarkably relevant.
Because, as the editors of the translation note, today's school mathematics is not very different from the school mathematics proposed at the time of Klein. It still holds up. So, okay, let's jump right into this central idea Klein put forward, this crucial difference between precision mathematics and approximation mathematics. Why was this distinction so important to him?
Well, Klein introduced this idea really specifically to bridge a critical gap, a gap that had kind of formed between pure mathematicians, the ones dealing with abstract proofs, and applied mathematicians, the folks working with real-world data. Precision mathematics, at its heart, it involves all those propositions logically deduced from axioms. Absolute truths like the rigorous foundations of geometry or abstract analysis. Approximation mathematics, though, that's different. It embraces results you get from experience, from observation, and it acknowledges that there's always going to be a certain degree of, unavoidable error in any measurement.
Okay, so it's like what we define perfectly in theory versus what we actually measure out here in the real world.
Exactly. That's a great way to put it.
That seems like a really powerful framework. Where do we, maybe just as everyday thinkers, get those two confused most often? And does Klein's idea apply to how we teach math, like to beginners?
Oh, absolutely. That's a great question. Klein and later the Italian geometer Guido Castelnuovo, they really emphasized that teaching for beginners, or, anyone just using math as a practical tool, should make a naive use of the intuitive approaches. What that means is starting with how concepts are formed from observation, how theorems can actually be verified in practice. It's essentially about integrating approximation mathematics right into early learning, letting students see how math connects to the world around them first.
That makes a lot of sense. Start with the tangible. But here's where, for me at least, it gets really kind of mind-bending. When we link numbers to points on a line, we instinctively assume this perfect one-to-one matchup, right? Every number gets its own unique spot. But Klein says this is where we step into the realm of abstract geometry, something beyond our everyday intuition. What exactly does he mean by that?
He means our intuition kind of hits a wall there. Take the example of rational numbers, fractions between 0 and 1. Mathematically, they're everywhere dense, which means you can find infinitely many of them in any tiny little subinterval, no matter how small you make it.
Okay, infinitely many. Sounds pretty packed.
It does. But, as Klein vividly puts it, the same subinterval is still riddled like a sieve, because infinitely many irrational numbers, numbers like pi or the square root of 2 that can't be simple fractions, they also need a place on that line. Our spatial perception, our ability to visualize, it just cannot imagine a set that's dense everywhere but still somehow does not exhaust the continuum. It's full, but also full of holes.
Wow.
The abstract definition is perfectly clear, mathematically sound, but the visual representation, it's basically impossible for our minds to truly grasp. It forces us to admit the mathematical ideal is way more complex than our senses perceive.
So, okay, we got the basic setup. Precision is the ideal. Approximation is what we observe and measure. But where this really starts to, I think, challenge our everyday thinking is when we apply it to basic geometric ideas, things like curves and functions. What does Klein reveal when we dig into these, seemingly simple concepts?
Right, because what we see when we look at, say, a curve drawn on paper or even look out at a distant forest, that isn't necessarily what precision mathematics defines. Klein introduces this concept he calls a function stripe. It's about how our visual sense works. There's this peculiarity. When we look at a huge number of small objects that are really close together, our brain kind of smooths them out. The idea of continuum arises within us, as he puts it.
Like seeing the forest as one connected green shape, not individual trees.
Exactly. Or maybe the blurred outline of something moving really fast. This perception of a curve, it inherently has a limited precision. It's not some infinitely thin, exact line. It's more like a band or a strip with a bit of uncertainty. That's the function stripe.
Yeah.
It acknowledges our senses perceive things with a certain, well, blurriness, not that infinite mathematical exactness.
That's a really powerful idea, the function stripe. Our brain interpolates, smooths things out.
Right.
Okay. But then we bump into something like the Weierstrass non-differentiable function. I remember hearing about this. It's continuous, right? You can draw it without lifting your pen.
Yeah.
But it has no defined slope anywhere. How does Klein explain that mathematical monster?
The Weierstrass function. Yeah, it's a classic mind bender. It's defined as an infinite series, a sum of lots and lots of cosine waves, basically. The critical insight is this. While the amplitudes, the heights of its component partial curves get smaller and smaller, their steepness actually rapidly increases if a certain condition between the parameters is met. So the approximating curves, if you just sum up a finite number of terms, they become increasingly jagged, sharper and sharper peaks and valleys.
Like trying to draw an infinitely detailed fractal, adding smaller and smaller zigzags constantly.
Exactly like that. It's an excellent analogy. And the crucial point is, if you try to calculate the slope, the derivative, at any point, it's like standing on an infinitely jagged mountain range. There's just no single well-defined direction because the terrain is constantly spiking up and down with essentially infinite steepness at infinitesimal scales. This completely excludes the existence of a finite or of an infinite derivative. This function pushes mathematics way beyond visual intuition. It forces us to confront the fact that what our eyes expect a smooth line to be, mathematics can rigorously prove is infinitely jagged. It defies our most basic sense of shape.
That is genuinely wild, a continuous function with no tangent, no slope. It really makes you question what a line even is, which brings up a fascinating point. How does this whole concept, precision versus approximation, connect to our understanding of natural laws, like physics? Are they truly exact, or are they maybe also approximations?
That's a huge question, and Klein definitely dives into it. Consider something pretty basic, like the law of projectile motion. You know, the path of a thrown ball. Physics class parabola. Observation confirms it works, yeah. But, as Klein points out, only in an approximate way. A real thrown object doesn't trace out a perfect mathematical parabola.
Right, there's air resistance, spin, all sorts of things.
Precisely. And any tiny deviations we measure, we tend to attribute them to disturbing factors or observation errors. Klein argues that the very idea of formulating the exact laws of nature by simple formulas comes from our desire to master external phenomena with the simplest tools possible. It's a powerful principle, he calls it simplicity or economy of thought, that guides scientific discovery. We look for the simplest mathematical model that approximates reality well enough for our purposes.
Okay, economy of thought. That makes sense. But if we're talking about precision, surely astronomy is the gold standard, right? All those calculations seem incredibly exact. How accurate is Newton's law of gravitation in practice, according to the work of the astronomer Simon Newcomb? Klein cites him, I think.
He does, and it's quite revealing. Even in astronomy, where precision is pushed to its absolute limits, Newcomb's analysis showed that Newton's law is confirmed by empirical data, but with surprisingly very limited accuracy. For instance, Klein mentions that for distances up to about 20 times the Earth-Sun distance, the uncertainty in the calculated force of attraction could be as high as 1/3, or maybe 1 part in 5,000 of the value, depending on how you measure.
1 part in 5,000. That sounds pretty good, but maybe not the perfect exactness we imagine.
Exactly. It's incredibly precise for most things, don't get me wrong, but it's not infinitely precise confirmation. It's not saying the law is wrong, but that the actual measurements, the experimental data, only confirm it within these margins of error. And of course, later, even Einstein's theory of relativity brought great progress and changes to this field, especially in explaining things like Mercury's orbit, which Newton's law couldn't quite nail down perfectly.
So even our most fundamental laws, the ones we thought were exact, turn out to be incredibly precise approximations confirmed by observation up to a certain point. Okay, this then leads to an even bigger, maybe more philosophical question Klein touches on. If we describe natural phenomena using analytic functions, you mentioned those are functions so smooth and predictable that knowing just a tiny segment tells you their entire past and future. Does that mean the entire future of the universe is predetermined, locked in?
Well, that's the logical endpoint of what Klein calls analytic determinism. If the motion of every single particle is governed by these perfectly smooth analytic functions, then yes, its trajectory in an arbitrarily small time interval would steadfastly determine the trajectory in all the following time intervals. It paints a picture of the entire universe unfolding like a perfectly designed, utterly predictable clockwork mechanism. Laplace's demon and all that.
Right. No room for chance or anything else.
But Klein also discusses an opposing view, one where trajectories might be determined not by the functions themselves being analytic, but by differential equations that have analytic coefficients. This subtle difference allows for something called ramification points. These are points where a particle's path isn't uniquely determined just by the general mechanical laws. He mentions Joseph Boussinesq, for example, who actually believed these extra mechanic causes could allow for things of a biological or ethic nature, maybe even free will, to interfere with the purely mechanical order, a sort of fork in the road not predicted by the initial conditions alone.
Whoa. Okay, so even within this mathematical framework, there's debate about determinism versus potential unpredictability. That's fascinating. This whole deep dive is definitely challenging my intuitive grasp of geometry. It feels like the more we learn, the less our everyday sense of curve or line seems to hold up. Let's talk about the piano curve you mentioned earlier, the curve that somehow fills a whole square. How is that even possible? A one-dimensional line filling a two-dimensional area.
Right. It sounds completely paradoxical. Imagine trying to draw a path that twists and turns so incredibly much within a square that it eventually touches every single point inside that square. It completely fills it. It's like, yeah, trying to draw a 1D line that somehow colors in an entire 2D area. Klein describes its construction as an infinite repeating process. You start simple, a square, a diagonal line maybe. Then you subdivide the square into, say, 9 smaller squares and replace the simple line with a more complex sort of hook shape, which is basically a scaled and reflective version of the overall pattern. And you just keep doing that, repeat infinitely. With each step, the jags in the curve become steeper and steeper, more and more intricate. The limit curve, C infinity, is what ends up continuously filling the entire square.
So it is a curve, mathematically speaking, because it's continuous. But it's not like any curve we'd ever sketch or intuitively think of. Does this mean our intuitive idea of a curve is just too simplistic? Is there a more, reasonable mathematical definition that matches our intuition better?
Well, yes and no. There is. The mathematician Camille Jordan defined what we now call a Jordan curve. Think of a simple closed loop, like a circle or an oval. A Jordan curve has the property that it neatly divides the plane into 2 distinct regions, an inside and an outside, with the curve itself being the boundary they share. That matches our intuition pretty well.
Okay, that sounds familiar. Inside, outside.
But the piano curve, even though it is continuous, does not satisfy Jordan's conditions. It doesn't divide the plane in that nice, intuitive way. It's just everywhere inside the square. So this really highlights how our naive intuition, as Klein calls it, often guides our terminology. We call the piano thing a curve, but it doesn't behave like the curves our intuition expects, which are closer to Jordan curves. Precision math allows for stranger things.
That's fascinating. But then can we even perceive these different types of ideal curves differently? Like if someone showed us a computer plot, could our spatial perception actually distinguish a perfect circle defined by its formula from this mind-bending piano curve defined by its formula?
Klein argues, pretty strongly, no. He says that in both cases, we can only mentally determine the position of single points with restricted exactness. Our perception is inherently limited. It doesn't intuitively grasp the infinite subtleties, the different kinds of infinite processes involved in constructing these idealized mathematical objects. The very concept of curve, in its full mathematical richness, goes way beyond what our senses can directly intuit or differentiate just by looking.
Okay, so these abstract concepts really push the boundaries of our intuition. Let's try and ground this back in the real world again with practical geometry, like land surveying. Measurements there are never perfectly exact, right? There's always some error. What happens in something called the Snellius problem? I think that's where you're trying to locate a point using angle measurements from known reference points. How does approximation play in there?
The Snellius problem, yes. It's a classic surveying task. You're trying to find your position, point P, by measuring the angles to 3 known points, A, B, C. Now, mathematically, there's usually a unique solution, but practically, it can be critically affected by what's known as a danger circle. This is the circle that passes through the 3 known points A, B, and C. If the point T you're trying to locate happens to lie on or very close to this same circle, well, the geometry makes it impossible, or at least extremely difficult, to determine its position accurately.
Why is that?
because many points near that circle would give you almost the exact same angle measurements back to A, B, and C. So even tiny, unavoidable inaccuracies in your angle measurements can lead to huge errors in your calculated position if you're near that danger circle. It can be fatal, as Klein puts it, for determining the position reliably. This leads geodesists to think about things like precision curves. Lines on a map where all the points on that curve would have the same expected mean error in their determination based on the geometry. It's a very practical consequence of approximation meeting theory.
Right. So in these practical applications, the rigor of precision math definitely bumps up against the messy reality of measurement error, of approximation. How do geodesists, the people who measure and map the Earth, deal with the fact that the Earth's surface is obviously inherently irregular? It's not a perfect sphere or ellipsoid like in the math books.
That's a huge challenge for them. They can compare the Earth's surface to an idealized ellipsoid, but only at large. So, for example, comparing the general shape of Central Europe to an equivalent piece of a perfect ellipsoidal shell, that works on a big scale. However, Klein points out, at a small level, zoom right in the surfaces do not correspond at all. If you tried to rigorously define a perfect mathematical tangent plane to the actual Earth's surface at some point, you'd have to account for every tiny bump, every hill, every valley, maybe even down to the molecular structure of matter, as Klein uses. It shows we're not really dealing with a smooth mathematical surface in reality, but more like a complex, rough space layer whose thickness loses relevance with respect to its extension. It's a fuzzy, thick boundary, not a sharp line.
That sounds an awful lot like our earlier discussion about function stripes, where our perception, or in this case, the physical reality, smooths out or averages the details. How does this fuzziness play out with concepts like a geodetic line on the Earth's surface? That's supposed to be the shortest path, right?
Exactly. A geodetic line on an idealized ellipsoid is a purely theoretical construct, the shortest path between 2 points on that perfect, smooth, curved surface. But in practice, geodesists work with things like geodetic polygons. These are essentially chains of straight lines, maybe polygonal chains whose sides are, say, 10 kilometers long, connecting points they've actually surveyed. So the critical question for geodesists, and really for approximation mathematics in this context, becomes: how much does this purely theoretical geodetic line deviate from the empirical measurable polygon that they can actually inscribe on or compare to, the ideal ellipsoid? Klein notes this is an area that, even in his time, still warranted more explicit study. It highlights that ongoing tension between the neat mathematical ideal and the messy, observed, approximated reality.
This leads perfectly into something else Klein mentions, Pascal's theorem in drawing geometry. He phrases it interestingly. If 6 points lie approximately on a conic section, and I draw their approximate connecting lines, then these points are approximately collinear. My question is, what does approximately really mean here? And how do you even measure or quantify that in a practical, graphical sense? Seems very vague.
It does sound vague, but there's rigor underneath. To make approximately precise in drawing geometry, especially for theorems like Pascal's, Klein points towards using differential formulas. These formulas basically quantify how small changes, small errors in the coordinates of the initial points affect the final result. In Pascal's case, the result is a determinant that should be 0 if the points are perfectly collinear. So the goal isn't that the determinant you calculate from your slightly inaccurate drawing is exactly 0. Instead, the goal is to show that it remains small for suitable input errors. You want the result to be close to 0 if your inputs were close to ideal. This provides the necessary theoretical foundation for the graphical execution. It gives you confidence that your drawing method isn't fundamentally flawed by small imperfections. Klein also makes a side comment here that our education often lacks independent tinkering and precise observation of concrete relations, which makes us prone to always accept without criticism the approaches that we find in books. It's a bit of a jab, a call to engage with the messy reality of doing geometry, not just reading about it.
That's a powerful statement about learning, actually. Engage with the approximations. It really feels like this whole discussion, this constant tension between the ideal and the observed, suggests our intuition can sometimes lead us badly astray, even on what seem like simple geometric problems. Can you give us one final, maybe striking example of this that Klein uses, where intuition fails but precision math clarifies?
Definitely. He gives a great one. Take a simple, closed, convex curve, like an oval shape, and intersect it with a straight line.
Okay, easy. 2 intersection points, right? That's what intuition screams.
That's what intuition screams. And in precision mathematics, that is guaranteed. If the curve is a regular idealized curve, meaning it has a well-defined slope and curvature everywhere, and it's everywhere convex in the strict mathematical sense. However, Klein says, what if we were to replace that simple oval with something like a Weierstrass curve, or even conceptually a piano curve segment? Remember, those are continuous but incredibly complex, lacking consistent slope or curvature. In that case, the idealized mathematical figure could, surprisingly, have 3 intersection points, or 5. Always an odd number, it turns out, under certain conditions.
Wait, 3 or 5 points where a straight line crosses a closed loop?
Because the curve is so infinitely jagged or convoluted, the line might pass in and out multiple times in an infinitesimal region. Yet the empirical figure, what we would actually see if we tried to draw or observe such a thing, might still only appear to show 1 intersection point, maybe 2, because our perception, or any physical drawing tool, averages out all this infinite tiny jags. The proof for why it must be an odd number in the ideal case, Klein emphasizes, has to be based on concepts and axioms of precision geometry, not just on looking at a potentially misleading picture or trusting our gut feeling. It's a perfect example of where intuition fails and precision math reveals a deeper, stranger truth.
Okay, wow. You've just taken us on quite a deep dive into Felix Klein's profound distinction between precision and approximation mathematics. We've seen how this core idea really challenges our everyday intuition. From the sieve-like nature of the number line, packed yet porous, to continuous curves that can somehow fill a square or have no slope anywhere. And we've also explored how this distinction applies in very practical ways, from the challenges of mapping the irregular Earth's surface to understanding the unavoidable approximate nature of even fundamental laws of nature and basic geometric constructions. So here's a final thought to leave you with as you go about your day. Think about your own engagement with information, or just your daily observations. How often do you implicitly assume the precision of some ideal concept, mathematical or otherwise, when in reality, you're interacting with an approximation out here in the empirical world? Where might you be seeing a function stripe rather than an exact curve? Or perhaps assuming an exact law where only a highly precise but still approximate relationship actually exists? What new questions does this whole understanding raise for you about the very nature of knowledge itself and the limits of our perception versus the power of abstract thought? Something to mull over.